Good morning. My name is Stephen Badger. I'm the team lead for this project. We also have Paul Sheen, our sensor engineer, Hans, who worked on circuits and signal processing, and Zhang, who was our software engineer. We are EtherTech. We're a student-driven project that's interested in producing an Insole power meter. Power is an incredibly rich data source for athletic training performance. And so if someone is able to obtain the power data that they're outputting during running or cycling or some other activity, this can be useful for refining their training activities. So we created a device that's able to measure the power and then bring that to an MCU and then transmit that wirelessly over Bluetooth to a phone app. So Paul's going to talk more about our sensing.
So the sensor we have chosen to use is the piezoelectric transducer. This sensor is able to generate a voltage when it's subjected to a certain amount of pressure or any pressure at all. Over here we have shown how we distributed our sensors around the insole of the shoe to be able to measure the distribution of weight across the foot. So we characterize these piezoelectrics by using a universal testing machine which was located in the mechanical engineering department of our school. So the voltages from these piezoelectrics are sent into an op-amp where a DC offset is provided. This DC offset is 1.25 volts, and then the signal is attenuated and then sent to the analog front end. I'll now pass it to Hans to talk about the AFE.
Right, so after we figured out what sort of structure we wanted for our op-amp circuitry, we designed two different circuit boards, printed circuit boards, and had these produced by a couple of American printed circuit board manufacturers. One printed circuit board was just to house the op-amp circuitry for each sensor, so each individual sensor had its own printed circuit board. And then we designed a second printed circuit board to handle transmitting our data to the microcontroller and also providing the power rails for all of our op-amps. So we provided a positive voltage rail and a negative voltage rail to the op-amps in order to allow us to get the bipolar signal that is generated by the piezoelectric transducer. And we also provided that offset voltage that Paul was talking about. These are all fairly low power systems, which is important for our wearable device, basically important for its mobility and the long-term energy provision to the device. And so the analog front end handled all the data processing, and then the data processing was then passed on to the microcontroller, or the data lines were passed into the analog to digital converter of the microcontroller before being transmitted over Bluetooth. So I'm going to hand it off to Zhang so he can talk about how we handle the Bluetooth communication and app development.
The microcontroller communicate with an audio device with a Bluetooth low energy protocol. Data processing is done on the application side and based on our UTN testing data set, and the relevant results are displayed on a graphical user interface such as the instantaneous power measure, the average power measure over the whole section, and the power distribution over each sensor.
So we have more information about performance metrics and battery life and accuracy, but we can talk about that at the poster. In the meantime, can we answer any questions? Yeah.
Is this UTDesign or sponsored or your own project?
This is a student-driven project.
There are some commercial products that are pretty similar. Did you do a comparison to existing?
Yeah, so most of the power sensors that are available that are Insole-based calculate power indirectly. So they'll say, you know, you're going at this speed, you have this heart rate, and so we have a calibration curve that says this is approximately the power you're outputting, but they're not directly measuring the actual power that's being output. And that's the case for the market solutions that are out there. There is one other company that's doing something similar to what we're doing, but they're using piezoresistive devices, and so we were interested in using these piezoelectric transducers because they generate their own signal, their own voltage. They don't need a voltage running through them, and so they have lower power consumption.
What exactly do you mean by power? Pressure or?
In terms of what power are we measuring?
Yeah.
Yeah, so the way we characterized it was, well, do you want to talk about that, Hans?
Yeah, sure. So basically, you could think of these almost as serving as a load cell. They're measuring sort of the force times distance that's being applied on top of the sensor. Transducer is just an energy converter, so they have some sort of energy efficiency. So basically, what we were doing with the universal testing machine, it's able to measure a certain amount of work that's being exerted onto the sensors that are available on the testing machine. and we were seeing how that correlated to the voltages we were getting out of the piezoelectric transducer. This basically becomes a field testable UTM in some respects. So we can measure the energy output based on the energy conversion from the piezoelectric transducer, and then use that to generate a power number saying that this is about how much power you're putting out as a user. This is a little different from a lot of power meters that you'll see on bikes and things of that nature, because they can draw upon some just simple mechanics and deal with things like torque and say, okay, this torque will translate to sort of a amount of energy going over time. But this is just sort of more, I guess, along the lines of something that you could see using a load cell.
How did you simulate all the devices together? Did you simulate the whole system?
Yeah, so-
How do you do that to pick what you're going to use?
As we were working with the universal testing machine, we were also gathering the voltage data that was coming from the piezoelectric transducer using an oscilloscope. And so we were able to use Linear Technologies LT-SPICE environment to actually simulate how this voltage signal that we got from the real world, how it interacts with the electronic circuitry that we developed to figure out how the signal would be go through the different stages of our device. We also, just reading all the characterization data on the piezoelectric transducers, they provide you with sort of the parasitic capacitance and the parasitic resistances that are in there, or the series resistance that's present on the piezoelectric transducer, so we can model those as just voltage sources with these parasitics included. So yes, we did some modeling.
All right. I think we can thank our this team and move on to the next.